Good afternoon. When I looked to the CTBUH Congress synopsis, then I saw global urbanization, therefore clear need for skyscrapers. Also skyscrapers for gains in land and infrastructure efficiency. And at the same time, there was a warning or some questions. Is the skyscraper a sustainable building type? And can tall buildings reduce and harvest enough energy to become carbon neutral? And that is then also the talk of my presentation today. Well, definitely when we look at a building like Heron Tower, very close to London Liverpool station, there's a lot of public transport connections, so we can have a discussion about tall buildings which are located very close to transportation. Unfortunately, I don't have any knowledge about this. And what I would like to discuss today is what can the facade do in a tall building. Now, facades are the largest surface area in the building. So, and it is actually the interaction between the internal and the external environment. So there must be a role for the facade to achieve sustainable tall buildings. And, can skyscrapers be sustainable? Well, perhaps at one say we say no. Solar gain, excessive cooling, glare, use of materials, clearing and maintenance, and so on. So there is a lot of issues to tackle when you want to make the building sustainable. But on the other hand, we also have available natural daylight, visible comfort, view out, potential for solar energy generation. So there is a big contradiction between factors that are influencing, yes, we can make sustainable buildings, otherwise no, it will be a difficult part. So I thought, definitely when we look at certain countries where more stringent regulations have been put on, energy regulations, also clients that ask more and more for comfortable buildings, and we see that there are a lot of developments gone for advanced facade technologies which have led to more sustainable high-rise buildings. So also our company has developed a new facade typology, is a MFREE-S closed cavity facade. So I thought, yes, this topic might be interesting for this conference. So thank you very much, people from the CTBUH, to give us this opportunity to speak here today. So I will speak especially about sustainability and all energy and environmental issues and related the closed cavity facade. So I will tackle different facade types together with this new developed closed cavity facade. I will also show that software tools can be useful for a holistic design approach and validation. The impact of the facade type and their properties on the energy and comfort of the building performance, some project applications and a decision-making matrix, and hopefully we can come to some conclusions that we can discuss later on after the session. First of all, Permis Lisa Group. Well, we are one of the leading contractors in engineering, project management, manufacture and installation of architectural envelopes and interiors. And what we are looking for is special feature buildings. We are world presence with more than 50 companies in 28 countries and 12 production plants with a turnover of 1.1 billion. And I will not speak more about my company. There is a stand and people who have questions can go there. I would like to focus today on the technical issues. And our company activities, we are doing from a scratch white piece of paper. We're doing the design and engineering, the manufacturing and the site activities. So basically from zero to the full development of the facade system on the building. These activities happen in a company of the different companies. We also have a focus in our company that is in excellence of new technological solutions. And for this, we have a research group which is cooperating also with different specialists in the world. And our focus areas are energy comfort and renewable energy, acoustics, bomb blast and other security matters, fire, alternative materials and new design processes. Tomorrow, my colleague Bert van der Linde will speak about the different technological solutions in the area of design and security. Today we will focus on this area, energy and acoustics and renewable energy. A building physics person looks at facades perhaps in a different way than an architect, and you can see it already here on the images. He's trying to look at some kind of separator for the thermal insulation between inside and outside, basically trying to overcome or use the interaction, the dynamic interaction of the external environment, being the temperatures that go up and down or the solar radiation, and trying to make sure that internal space is accommodated as best as possible. We have different types of facade systems, single skin facades, for instance here, double glazing with internal blinds, external blinds, some louver systems. We can also go to double skin facade. That means we have the same traditional facade system, but we add a single layer at the inside, for instance, with the blinds integrated between the two facade skins, or we place an additional skin to the outside where we have the blinds in between, but we then ventilate, for instance, to the outside. Here, this ventilation is done in an active wall with a mechanical ventilation system, which is actually sucking the air through the cavity. And in this situation, the ventilation is happening by natural ventilation. We can also put some microfans in there to assist this ventilation. And then finally, we also have MFREE-S closed cavity facade. Well, that is a double skin facade, double glazing to the inside, single glazing to the outside, and with some blinds in between. And in this way, we can arrange the solar radiation and the temperature from the outside. The natural ventilated facades or facade typically with a deep cavity so that you can also ventilate the internal space. The interactive facade system and the facade respirant and the MFREE-S closed cavity facade, they don't need more than just the depth of your framing, which you need for structural reasons. So you're not going to make the facade much heavier than required for structural reasons to withstand wind loads. Some examples, single skin facades like the World Financial Center, Beekman Tower, active facade, Morehouse, interactive facade or natural ventilated facade system, the Post Tower or Torrey Crystal. Here you can see that you can also open the internal double glazing window, and also the external single skin facade can be opened. And then finally, the closed cavity facade, of which you see an early adoption, the Roche Diagnostics in Switzerland, where you have a single skin and an internal skin, a double skin, a triple skin in this situation, in order to do this thermal barrier. When we consider single skin facades and we have internal blinds, we know that we have some special issues, like for instance, the energy consumption. In the winter, you lose a lot of heat when you're heating. In the summer, you gain a lot of heat because if the blinds are inside, the heat is trapped and cannot go out. We can also have issues with glare and acoustics with high transparent buildings. And in this presentation, we will try to find some solutions. If we stay in the single skin facade systems, then of course we know that clear glass in order to protect yourself against solar heat gain is not sufficient. So the glass, clear glass is transparent for shortwave radiation. So the sun heat is coming into the building, then it is absorbed by the materials, and then it will re-radiate it to the environment. The same happens with internal blinds. If it hits the internal blinds and the heat is absorbed, it is trapped and it can difficultly go out. We call this the same as the greenhouse effect, and we need to do something about that. We can use tinting, coating, selective glazings. They are very good in order to block the sun, but the problem is they are very static. And I can show you later on the advantages of using dynamic systems because you can optimize. If I look, for instance, at this building today, there is a lot of diffuse daylight at the north, the east, and the west today, and you want to use that daylight into your building. Now, if you use selective of coating or tinted glazings, you are blocking all that useful daylight, and it's not coming into the building, so you have the electricity on all the time. Actually, you only need some blinds to protect yourself from the glare, now at this moment at the south. Also, if you look at it, it's very diffuse. There is quite some mist, and you would actually like to have as clear glass as possible at this moment in time at these orientations. Passive control glazings have an option. They will change their properties, but the problem here is that sometimes the solar gain is useful, sometimes it's not. So you're blocking actually sometimes the solar radiation while you could use it. And then also the appearance is questionable when we speak to architects. Active control glazings, for instance, electrochromic glazing, is coming up very fast, very popular in America, and has very useful properties. When the electricity is switched on, they become transparent, and then the light can come in. You can make use of the daylight. And then when you switch it, then it blocks the sun, and then there is less solar gain and also less glare problems. The only problem with the glazing up to now is the long-term performance, the guarantee, and also the cost for this material. But as we are going to use it more and more, it's definitely something that is to be considered, for instance, skylights and so on, to keep an eye on. External shadings, when we want to block ourselves from the sun, are very useful. So either we can have lightweight versus robust shading. I will show you later on here some screens, lightweight screens put on the external. You can see you can use them, you can automate them so in order to protect the person of the solar radiation. But you see here at the outside a flag, as soon as the wind is too intense, the blinds go up and the user is sitting in the direct sunlight, having problems with glare and also overheating of the building. You can use a secondary screen at the inside to block yourself from the glare, but then still the heat is trapped inside the building. If you're looking to environmental solutions that are really making a success, then we need to have more robust systems. Also here, Venetian blinds. Here you can see a building. It's not a high-rise building, and still, and you have already these effects. You can see what the purpose is. So they want to have external shading in order to block yourself of this intensive solar radiation. You can see after a couple of years that some of these shades were not performing very well. And in the end, you can see here are the original shading devices. They have put here some reflective blinds inside the building because the external blinds were broken. Then some other person has done something similar but with another type of material. And if you see carefully, there is a man trying to do something similar but perhaps with, again, another one. I think for the architect or the client, not really what he intended in the beginning. So you have to be very careful of using lightweight external shading devices. And if you put a single glass screen in front of it, you protect them against the wind loads. You protect them more against the dirt. And in this way, lightweight shading devices can operate properly. If we look at heavyweight or more robust shading devices, like for instance here, the Gardner office in Gundelfingen, it is a very environmentally friendly building, but you can see that in order to control the blades, also everything has to be more robust. And when we apply this on a high-rise or a tall building, then we can already immediately feel that it's not always the best solution, and so definitely not when we look at cost effectiveness. Here we can see a closed cavity facade. So basically it is a lightweight facade. It is as deep as a normal facade system. Single glass to the outside, a double glazing at the inside, and some blinds in between. Of course, we have talked about the greenhouse effect. In effect, you create a greenhouse effect as well in this cavity. It is the blind this time that is absorbing all the heat, but because the thermal insulation of this glass is much more inferior than what we are building at the inside, double or triple glazing, you block all that heat up front and it's going and you drive it to the outside. So instead of having your greenhouse effect in your building, you have it now in your cavity and you avoid having that energy coming in. So we know from double skin facades, which we have built in the past a lot, they have a high energy performance, high visual comfort, acoustic performance, and protection against solar heat gain. Now this closed cavity facade gives you the additional benefit that you don't have to maintain as much into the cavity. Either you have to go inside to clean it, when people in the building don't want to have access from cleaning people, or you avoid having to open the window doors in order to clean because you prevent it from getting dirty. Well, the only thing you need is a pressure system that is connected to each facade system. It's a simple compressor with a dehumidifier. You connect each tube, a small tube, to the facade system, and in this way you keep it clean and avoiding condensation. We have done a lot of testing on this. You can see here testing in the Netherlands on durability, outside measurements. Also, and you can see, perhaps appreciate the shape of or the size of this testing equipment. we can turn this one towards the solar radiation and follow the sun with a sun tracker. Here you can see the people, so it's enormous, so we can test full-size elements. And also we have done dust, sand, and heat environment tests in Dubai in order to look how the facade will be performing under these aggressive dust production. And finally, last but not least, we have a full-size accelerated testing setup, so we can test for any climate in the world in order to see how the facade system is working. Now some results. If we look at, for instance, the surface temperature, as I was saying, the blinds are heating up with an internal blind. When the sun is hitting this blind, it is heating up. Here you can see it can go to 50 degrees. If we look to a closed cavity facade, the blind will only heat up to about 30 degrees. So there's a difference of 20 degrees in temperature. No wonder that this facade is much better in terms of thermal comfort and in less energy gain into the building. So you will have to cool much less with this kind of facade system. Testing done in order to calibrate our simulation tools, because in practice you want to simulate performances of any building in the world in order to predict the performances up front. And we can see a very good correlation between the test and the passes cell and the simulation tools that we have done. If we now look at the energy performances, so we use our tools in order to predict the energy the impact of the facade choice on the energy consumption in the building. So we use the weather data, temperatures and solar radiation. We take a zone into the building just to have a look to that one. And we can use dynamic controls in there. We can use, we can set for different activities, the heat loads into the building and so on. So basically, we consider here at the top different facade systems: single glazed unit, double glazed unit, double glazed units with a high performance coating. I think you call it double low E or double silver low E and triple silver low E in Asia. Also triple glazed unit, active wall, interactive facade, and then also finally the closed cavity facade. And we can look at the different performance criteria. These are the steady state performance criteria: typical U value, solar heat gain coefficient, light transmittance, the typical performance criteria that you agree on when you do a job. And then regulations are also highlighting requirements for these steady state parameters. Now, when we have a look, for instance, say if you go from single glazing to double glazing, okay, you save a lot of energy, we know that. This is for a London climate. So, of course, you can reduce the heating of that building enormously. When you go from a low E double glazing unit, low E, to a high performance double glazing unit, you again reduce the energy consumption significantly, and that is of course because you have a high cooling consumption. Offices, modern offices with a lot of glass or with an internal heat loads, they consume a lot of cooling. So you're effective with double low E coatings. When you go to a triple glazed, some countries would like to go to triple glazed units, you can see that you don't save so much on the cooling load. You can decrease for London climate a little bit further, but basically it's not an effective way to reduce the solar radiation, to reduce the energy consumption. When we look to active walls, interactive walls, we can see definitely for all the facades where the blinds are close to the outside that they are very effective to lower the cooling energy into the building. And here you can see the closed cavity facade. It is a little bit worse than a ventilated double skin facade in terms of cooling energy, but you reduce a little bit on heating energy, so basically you have this similar performance. Now, a lot of specifications are written for U value. Lower the U value as much as possible. You can see here that the U value of a triple glazed unit is better than the one of a closed cavity facade, but you see at the energy performance that this is worse, and this has to do with when the blinds are closed, that the solar heat gain coefficient, or the G value, is much lower for a closed cavity facade than for a triple glazed unit. Now, if we move ourselves to for instance, PERT office, and we are going to play with the light transmittances of the glazings. So, because PERT has a lot of intensive light, you need to block yourself to a certain degree from that even diffuse lighting. And if we look at the energy performances, first of all, let's have a look to a single skin facade with internal blinds. This has a light transmittance of about 60%, and we can see that we're using a lot of cooling in PERT, and that for instance, lowering the U values between an air-filled or an argon-filled solution will not bring you a lot on energy performance. If we compare now the clear glasses with the dark glasses, and I go up to 20 or less than 20% of light transmittance, so very, very dark glass, then what we can see is that we can reduce the energy consumption a lot. Now, the strange thing is, as soon as you go to closed cavity facades, that you can even go up to a light transmittance of 63% and still have better energy performances than, for instance, the dark single skin facade. And that is again because you're blocking the solar radiation before the double glazing unit. What you can also see is that the performance is even better, but that the performance, the energy performance of the building is not determined anymore by the light transmittance of the glazing. So you can vary the light transmittance of the double glazing as much as you want. You will not have a big effect on the energy performance. So that means you can go to more transparent buildings in order to leave some daylight in when you want it, or to see out during the night and block it when there is intensive solar radiation. Acoustics, some buildings, high-rise buildings also, like we said earlier, transportation, so they are built in areas of a lot of traffic. I will go a little bit faster on this one, but basically when we are looking, basically when we are looking at, it's because we're speaking about acoustics that basically, when we were testing different facade types, we can see that the RW value, or the weighted single value of the sound reduction index, is the highest for the concrete. And as soon as we start filling in windows, this is the weakest point, so we have to concentrate on the weakest point. Well, the double skin facade or the closed cavity facade have an acoustic performance the same as concrete. So yes, the double glazing unit or the glazing, your glazed element is not the weakest point in your facade on the acoustics anymore. We can also see that on the different frequencies. The first one is the green, is just a double glazing unit. When you use acoustic PVB layers, you can improve a lot at the higher frequencies. When you are using a closed cavity facade with a small additional cavity, you can increase a lot in the lower frequencies, which is interesting. And when you are going to a deeper cavity of 600 millimeter, you can increase again. But you have to be careful with this one. This is measured and simulated for a closed deep cavity double skin facade. As soon as you make perforations, you lose again at the higher frequencies. So in this way, you can conclude that the closed cavity facade is a very good acoustic barrier against outside noise. Now, just a small couple of slides for some project applications. These are the buildings we have done in the UK, in London, at Canary Wharf. All the facades are the same. We can say already something about the light use. Perhaps here is only one switch for the whole building. And here we have it in some of the areas. But definitely not an optimized lighting and energy consumption solution. If we look at the Heron Tower, and all the facades in these buildings at the time were high-performance double glazing units. But basically, there was no consideration on orientation or use of spaces. If we look at the Heron Tower, the way we have worked together with the client, the architect, and the consultants in order to come up with a holistic solution, there is at the north facade, there is a very transparent double glazed unit used in order to allow a lot of daylight coming into the building. At the south, as this building had to generate 2.2% of energy, we have put at the south photovoltaics. Also, all the lifts and so on are based in this area, because we know when we do our analysis that the highest consumption of energy is actually at this orientation. At the south-facing photovoltaics. Now, what is the interesting by lowering all this energy is by if you have to, as a client, have to put 2.2% of renewable energy on your building, which is very expensive, then the best thing to do is to first of all lower the energy consumption of your building, because 2.2 of an energy consumption which is much lower is a serious benefit for the client. So now we see that using advanced facade systems suddenly have an easy payoff because of the request of renewables on this building. I'm not saying that you only have to do it for that reason, but just to highlight on this specific project. So the final conclusion was at the north facade, double glazing unit, transparent, to get the diffuse London light coming into the building. At the east and the west is used the thin double skin facade. And at the south facing, there were the solar photovoltaics, about 3,000 square meters of photovoltaics in order to make energy generation. And then the final project, UCLH, is one of the first closed cavity facades that we have used. It is a hospital. There were very specific critical requirements, stringent energy regulations. They wanted to have, as the first hospital, to get the green label. So everything was really focused on that one. At the same time, they want to have high comfort requirements for patients and for the personnel. They are surgeons there operating, and they want to be in a very nice, comfortable environment. Also for the patient, it's not always nice to be in uncomfortable situations if you have to undergo these kind of surgeries. And then low maintenance was really an issue. They didn't want to have external shadings there as well, and the architectural appearance. We come up with a decision-making matrix, and for this project, high-performance coating was considered, high-performance coating with external and internal screen, but this was objected by the maintenance. We then have also an active facade system, interactive facade system, and finally the closed cavity facade. And you can see that the traditional facade, they fail on cooling or on maintenance, whereas the high-performance coated active facade system failed on condensation risk, and then the mold grow and the bacteria forming where they were scared of. And finally, it is the closed cavity facade because of the low maintenance and the long-term maintenance cost, which was considered to be the best facade system. The project, the closed cavity facade research project is finalized. It's now 2 years ago, and since then we have projects where the facade is applied to. First in a research center of Fraunhofer, a leading research institute for energy. Then we had this project Roche, where we have architect wanted to have a diagrid very close to the facade. They didn't want to integrate it into the facade system because you have a lot of issues of heating up of the structure. So they have placed it with a very transparent facade system, the structure just before, or the whole package before the diagrid. And this way you can see the facade system. And now it's the third Roche building we are doing. It's the highest building in Switzerland. It will now be built, Hochhaus. And then we have a couple of other projects. We start with smaller projects in order to make sure that the facade system is working very well. And now we have gone through that process. And here to show you, also in Shanghai, there is the first small project applied. So now some conclusions. If benefits of tall buildings are targeted, visual, daylight, and all the other benefits, then single skin facade will face difficulties with compliance with the regulations in the future, as this is already the case in some European countries. Use of automated blinds, double skin facade, and closed cavity facade technologies have a better energy performance. Advanced detailed dynamic whole building simulation tools have the benefit in order to show where you want to tackle the solution, not just on U value or solar heat gain coefficients, but really as an energy output. And then finally, the benefits of the closed cavity facade is that energy saving, occupant comfort, lower maintenance and repair cost, and thus a higher effective net level area with a high durability and therefore a lower cost. I'm happy to take some answers. Thank you very much for your attention.
Thank you very much.